Hello guys, am I visible? Am I audible? Hello, Banaras. Banaras vlog wala. First contest. Yeah, it didn't go well for me either. Hello. Okay, so I think I can share my screen now. Just one minute. Today contest is very interesting, especially the C problem. Yeah, what do you mean you solved all four? Yeah, I did solve the four problems, but during the contest, I was having some error in the C problem, which I could not debug during the contest. So, in a nutshell, I will have a very big negative delta, at least 100. Okay, presenting everything. Okay, my screen is visible now. Where is rank in today's contest? I don't know. I did not look at the rank. If I can't solve all four, I will have a negative for sure. Anyways, let's start the PCD. Before the PCD, let's talk about TLE eliminators. So the ones who have been conducting these PCDs, or the ones who have been making sure that these PCDs happen, is TLE Eliminators. And TLE Eliminators does have two free resources. One of them is CP31 sheet, which I think a lot of you guys would know about, where you are having difficulty-wise problems for every difficulty. And nextly, these PCDs, which you have been attending here. Along with this, TLE Eliminators does have a lot of courses as well, specifically for 4 levels. The first two are beginner friendly. The next two are gonna be a little advanced, especially the fourth level. So I would suggest you guys to check them out once. And you can go to the TLE Eliminators website, then click on courses to check out the 4 levels. Then click on explore now for any course that you want to check out, where you would be able to see the syllabus that would be covered in it, all the things that would be covered. And yeah, the main USP for the uh, TL Eliminators course, the main reason why a lot of people buy the course is for the doubt support, because here you will have a lot of experts and candidate masters who would be clearing your doubts, and you get doubts like almost instantly. I think within 1 2 minutes you will get someone to take up your doubt and help you out in solving the problem. So yeah, this is something I would recommend you to check out. Uh, let's begin with the first problem. Smallest index with digit sum equal to index. So the problem says that we are being given an integer array nums, and we have to return the smallest index I such that the sum of the digits of nums I is equal to I. If no such index exists, then return -1. So This is a very straightforward problem. It says that you are being given an array. Oops. You are being given an array nums of size n. You want to find out the smallest index I such that the sum of digits of nums I is equal to I. And as soon as you find out, like for all the indices for which this thing is true, you have to return the smallest value. So the idea is very simple. You have this array, just iterate from left to right, and for every index, just check if this thing is true or not. And for the first index where you realize that this thing is true, you can just return that value of I. So the main task of the problem is to just find out the sum of digits of a number. If you know how to find out the sum of digits of a number, you should be able to solve this problem. And doing this task is also very simple. I think we do get to learn about this at the very initial stage of our CP journey, not CP journey, but for the programming journey. Let's say you have a number like 94287. Then for finding out the sum of all of these digits, you can do something like um, have a sum variable initialized with 0. In that variable, add the last digit of the number. For finding out the last digit of the number, let's say you have a number n and you want to find out its last digit, you can just take its remainder with the number 10. Just divide it with the number 10, and the whatever remainder you get, that is gonna be the last digit, for which you can write something like this in C++. So this is how you can get the last digit, add it to your sum, and then remove this digit from the number. For doing that, you can just divide the number by 10. If you have a number, let's say 94287, and you divide it with 10, since both of these are integers, then so in languages like C++, the like the output you will have is gonna be 9428. Whatever comes after the decimal part would be removed, right? So you can just do something like, first of all, find out the remainder like this, and then divide the number by 10 to remove the last digit. Keep on doing this thing as long as the number has at least one digit, has at least one non-zero digit, right? So while the number is greater than 0, you can do this part. Okay. So, oh, by the way, you don't have to uh, assign the last digit as the number. This is just something we do if we want to find out the last digit. Like you can do something like n mod 10 only. That will give you the last digit without updating the value of n. So you can say sum plus equal to n mod 10, and you will get the last digit. Then divide n by 10. So that number will eventually become 0 and the loop will break out. The time complexity for this part is we go of log 10 base n. So if there is a number n somewhere around 10 raised to the power 100, then the time complexity would be only around 100 iterations. Right, it will have only 100 iterations in general. So time complexity is the go of log 10 base n, sorry, log n base 10. Yep, exactly. We just had to do simulate. We just had to simulate the problem. Whatever you are being told, just simulate this thing and you would be done. So for I equal to 0, numsci, and like for every element here, I'm having a loop from first element to the last element. Then I'm having this part to find out the sum of all of the digits. And then I will check if the sum of digits is equal to I or not. Return I if it is equal, and then return -1. Okay, simple enough. Now the things that we can gain from this problem, this is specifically for the beginners. In case if you did not know how to find out the sum of digits, this is something you can remember for the future as well. Like you should understand how it is happening and you should remember it for future as well, so that if you get something like this in future where you want to find out sum of digits for something, you would be able to do it very quickly. Nextly, here is an interview tip. If you are being given a problem like this in an interview, then please do not update the value of num_sci directly, because whatever vector has been given to you, if you just update that vector for finding out the smallest index, then the interviewer would not be happy, because this nums array might be required at some other place. So it's better to first ask the interviewer that, can I make changes to the array or not? And in general, for a problem like this, you should just create a new variable nums, like val or something. Maybe you can even name it as x, since the function is going to be very short. And instead of using nums everywhere, you can use val. So this is mainly for interviews. For competitive programming, you don't really need to um, focus this much. Like you can directly update this value. It won't have any trouble here. Like just verify that would you ever need the value of nums after updating it? And you need to verify this much as well, even for competitive programming. Okay, find using a function. Yeah, third one, it's not tricky. It's actually pretty standard. I will tell you about a way in which you should have approached or you can approach, and it is something you can just remember for future. Okay, nextly, as somebody suggested, for interviews, like even better thing you can do is just create a function, let's say with name sum of digits or get sum of digits, something like this, which will take an integer x as input and it will do this stuff and return it. So at this place, you could have just said get sum of digits of nums I. If it is equal to I, then return I, otherwise not. And this whole logic would be shifted to this place. So you can do something like this. And yeah, it might look good, it might not look good. Like in general, this is a good idea only. We can just create a function that takes nums and as a parameter for interviews. Yep, exactly. By the way, in an interview, you don't even need to write that function. For big problems, you can just directly use something like get sum of digits or of whatever, and tell the interviewer that, hey, I can create this function. Yeah. In most of the cases, the interviewer would probably not ask you to implement that function, since it's a very beginner friendly thing. So in some interviews, you can actually save time by not writing that logic and just tell the interviewer that, hey, I can write this thing, but I'm not writing it for saving the time. Or maybe just ask him, do you want me to write it, or is it okay if I don't actually implement it for now? Okay, let's move on to the second problem. Minimum swaps to sort by digit sum. In this problem, we have been given an integer array nums of distinct positive integers. You need to find the array in increasing order based on the sum of digits of each number. If two numbers have the same digit sum, the smaller number appears first in the sorted order, right? So you basically just need to sort the array. In case if there are, I will just explain it later. For now, or maybe I can explain it here. So this is the second problem. The problem says that we have been given an array nums of n integers. Let's say the nums array looks something like 18, 43, 34, and 16. Then in that case, you want to sort it in a way such that the people coming on the left side will have smaller sum of digits. Like in this case, the sum of digits of 43 is 7, whereas the sum of digits of 18 is 9. So this guy 43 should come on the left. And in case if there are multiple people having the same sum of digits, then the smaller number should come on the left hand side. and you know that all the digits are unique. So this like there will be no tie in terms of the value of the numbers. So the whole idea is, if I pick up any two people, let's say the left guy and the right guy, then sum of digits is the first criteria on the basis of which I'm sorting, and the second basis on which I'm sorting is the unique value, or basically the value of the number, right? This is gonna be used as a tiebreaker. So for this array, after sorting it, it would look like this. First of all, let's find out the sums. The sums of these digits are 7, and the sum of this number is 9. So in the sorted order, obviously these people should come at the first three positions, and this guy should come at the fourth position. Now among these three people, the smallest guy should come at the front, the second smallest at the second position, and the third smallest at the third position. And obviously this guy is at the fourth position for now. So after sorting the array, it should look like 16, 34, 43, and 18. I hope it makes sense, guys. Your logic is incorrect, actually. Okay, so first thing that we wanted to do was just find out how we have to sort the array. Right now, I'm only explaining the problem. We have not started the discussion for the solution. Nextly, we have to return the number of swaps required to rearrange the elements into the sorted order. Okay. And a swap is defined as exchanging values at two distinct positions in the array. So what we have to do is, we have to tell how many swap operations do we need to apply to turn this array into this. Like, this is how we want to sort the array. This is the original array that we have. And we have to find out the number of operations of sort type that would be required. So in this case, like, these two people have been swapped and these two people have been swapped, right? So we have one operation here and one operation here. We are using two operations. Like, we can do it in two operations. And yes, the output is 2. So after sorting, the array should look like this: 16, 34, 43, and 18. Swap 18 with 16, 43 with 34, and obtain the sorted array. Thus, the minimum number of swaps required to rearrange the arrays to. The given array is pretty big, and the values are also big. So we will have to keep this in mind. Since n is as large as 10 raised to the power 5, so our solution should have time complexity of something like big O of n, or big O of n log n, or big O of log square n, or maybe big O of n square root n. It should look like one of these, most probably, right? Okay, so first things first, let's discuss on how will you sort the array. Like, how can you sort the array? So for sorting the array, if you know how to sort a normal array, like in a normal array, what we do is, um, if you have a normal array that you want to sort, you just say that a guy on the left index should be smaller than a guy on the right index. If you want to sort an array into ascending order, right now you can apply the same sorting algorithm. The only difference would be that you want sum of L comma sum of AL comma AL pair to be smaller than sum of AR comma AR pair, where this sum is actually talking about the sum of digits. these sum functions are talking about the sum of digits. So you want the pair of the sum of digits and the number to be smaller than the sum of digits and the number, right? In case if the sum of digits are equal, then this would be used as a tiebreaker. Otherwise, if the first guy is different in the pair, then the one with the smaller value would come on the left hand side, right? And I hope that everyone is clear with at least this part, that this is what we want to do for sorting the array. So one very simple way for sorting the array in this order is just create a function, just create an array A such that A of I is equal to the pair, that is sum of AI comma AI pair. Just sort the just create an array like this and then sort the array. And now obviously that array will be sorted in this order only. Does it make sense? Tanuj, exactly, that's what I've been telling. This is the simplest way in my opinion. You will just create a vector of pair of integers and then sort it. First make a desired array and then compare the nums array for different positions swap. And yep, that should also work. I think we can sort according to the sum of digits of elements. We can, yeah, okay. So the things that we have discussed so far is, let's say you had the array 18, 43, 34, and 16. So what we will do is, from this we will create, and like this was the nums array that we had, and we will create an array A such that we will have elements as 9 comma 18, then we will have 7 comma 43, then we will have 7 comma 34, and then we will have 7 comma 16. So now if I sort this array, it would be sorted like this. For the people who are having the first elements equal, they would be having the smaller guy first come first. So 7 comma 16, then this 7 comma 34, and 7 comma 43, and then this 9 comma 18, because this is coming at the end because 9 is greater than 7, right? 9 is greater than 7. So this is how everything would be sorted by default if you just create a vector of pair of integers and call the sort function. Another possible way for doing this task could have been something like this. um, you can use a custom comparator. If you don't know about custom comparator, um, custom you can write your own custom comparator for sorting the array in this order. If you do not know about this, then I would recommend you to search about this. You will find out some Geeks for Geeks articles, some good ones, simple to understand as well. And in case if you do know about this, then this is up to you whether you want to use this or whether you want to use the array. Um, by the way, if you want to use the custom comparator, you uh, might need to be a little creative, because directly calculating the sum of digits inside the custom comparator will um, be inefficient. It will turn the time complexity into something like big O of log square n, which should also work for this problem, but it would be a little inefficient in comparison to the best possible approach that we can have. Okay, in a nutshell, like for now, I'm assuming that you guys know how to sort the array for now. Okay. I have told you a simpler way. I have told you a better way also. And there is an even better way that I would show you in the implementation. The implementation would be pretty neat for with that approach, but pretty good. Um, for now, we know how to sort the array. When I sort the array, do you guys agree that I can create a mapping like this? The guy 16 should come at the 0th position, like the 0th index after sorting the array. The guy with value 34 should come at the index 1, 43 should come at index 2, and 18 should come at index 3. Right. I can create a mapping like this one. I never really cared about the original sorting of the array I will have. I only cared about the finding about the places where the people should come from. I had this array, है ना? So I just want to know where this guy will go after sorting the array, where this guy will go after sorting the array. So I will make swaps to make sure that these people will reach the positions where they want to. Does it make sense, guys? We were getting some compilation errors. I don't know about that. If it was something related to static, I don't remember. Like I always create lambda functions, so um, I don't get any problems related to class. But when I used to create separate functions at that time, I used to get some problems related to class. And I think it could be solved by using a static keyword. Okay, Atharv, I can't really provide you a Java code. For Java code, what you can do is you can go to this solutions tab and then look out for the people with the Java code. But here at least you can understand the logic part. I will explain you the logic for now. So for now, can I say that I had this array 18, 43, 34, and 16, which I want to transform into 16, 34, 43, and 18. Can I say that this is equivalent to the task if I had elements like um, if I had elements like 3, 2, 1, 0, and I wanted to swap this I wanted to convert this array 3210 into 0123. Do you guys agree that this problem is actually like both of these problems would be equivalent? Because at the end of the day, it doesn't matter whether this guy is 43 or um, 61 or 54, no, 52 or 61 or 70, doesn't matter. है ना? All that matters is at the end of the day, after sorting the array, this guy should reach the second position. And which position this guy should reach has already been calculated. है ना? So once you know that this guy should reach to this position, you don't actually care about this guy's exact value. Right? So with the mapping that we had done, if you look at the mapping that we had done, that was 18, 43, 34, and 16. You know, 16 guy is given the mark 0, 34 is given the mark 1, 43 is given the mark 2, and 18 is given the mark 3. So basically, with this mapping that we could have done here, we should be able to find out the like um, final positions that we want for these people. है ना? And now the problem can be actually said as I have been given an array having elements from 0 to n minus 1, and I want to sort this array in minimum number of operations where in one operation I can just choose two indices I and j and then swap ai with aj. Right. I can just say that the problem is like this now. Everything looks good now. Meaning we can sort this vector of pairs and then just count the misplaced indices. No, no, no. I'm not talking about counting the number of misplaced indices. For now, we have not discussed on how will you find out the minimum number of operations so far. But I'm actually focusing on the thought process, like basically breaking down the big problem into some smaller problem. So we knew that we want to convert this array into this kind of an array, right? So whenever I have something like this, I'm being given an array and I want to sort it into some particular order. then one thing that I do almost all the time is for every guy, I just find out what would be its position in the sorted array. And once I know what should be its position in the sorted array, now I will just treat the 16 as 0, 34 as 1, 43 as 2, and 18 as 3. है ना? Because even if I had this array as the original array being given, the number of operations required to sort this would be exactly equal to the number of operations required to sort this. है ना? As long as you are maintaining the relative ordering. You only care about the relative ordering, not the actual values. So it would be easier for me to think on what would be the number of operations required to sort this instead of like in comparison to how complex it would be to think about sorting this. Right. If you have smaller numbers, every number coming from 0 to some index element, let's say n minus 1, it would be easier for me to sort it now, or at least think about the logic part. As for the logic part, let's say you have any array 4, 2, 1, 0, 3, 6, 5, anything like this, and you want to find out number of operations required to sort it. This is a very standard problem. I will tell you about how you can do it directly. Like I will tell you about the two things. First of all, the way in which I got this idea, and nextly, you can just remember what we do for finding out this stuff, because you can get this kind of a sub problem in lots of problems. So the idea here is this 0 should reach this position, right? You want to find out the minimum number of operations in which this 0 reaches here, 1 reaches here, 2 reaches here, 3 reaches here, 4 reaches here, I think, 5 here, and 6 here, right? So to minimize the number of operations, obviously you would not like to do something like swap these two, then these two. And if you're not gaining anything from making a swap, then why do you want to make a swap there? The greedy idea that we would get will just recommend us that hey, um, try to make swaps from which you are gaining something. So make swap here, okay, which will make the array like this. Then you would like to again make some swaps so that people get to their correct positions. Like maybe make a swap between these two people, or make a swap between these two people and sorry, these people, and so on. है ना? So let's say you make a swap between these two. So you get a 3 here and a 2 here. You have got two people at the correct positions in two operations. This 4 should come here. So let's make a swap between them also. 1 will come here, 4 will come here. Again, this guy also got to its best position. Let's make a swap between these. So 1 will come here, 5 will come here. 1 also got to its correct position. Swap between these. So, no. If you make a swap between these, 5 will come to its correct position. So, make a swap. 6 will come here, 5 will come here. You again got one thing. And make a swap between these. So, 2 and 6 both will get to their correct positions. Right. Okay, we did it in this way. Now let's find out the number of operations we actually used here. There is one operation we used here to make the swap between 0 and 5. And we had used one operation here, right? After these two operations, we got two people done. Then we applied, we had two here. So I forgot. Sorry. I just forgot the order in which we had applied the operations. There is one thing that I wanted to show, but I messed up a little bit. So let's do it again. Make a swap here and pick up any people. Let's say you make a swap between these. So 0, 5, 1, 2, 4, 6, 3. Let's say you make a swap between these. 0, 5, 1, 3, 4, 6, 2. The people done here so far are 0, 1, 3 is done, 4 is done. Right. Okay, yes. Um, I was making a swap to make this 4 guy come to its correct position. Like that was my idea in the way I got this approach for the first time. I had the idea that hey, just um keep like take the people to their oh no, this is not at the correct position. Yeah. Okay, let me be really honest. When I had done this problem for the first time, I had this kind of an idea. Take the smallest guy to the first position. Then take the first guy to the first position again. So 5 will be here, 1 will be here. Take the smallest guy to its correct position. Basically, I tried to think about some selection sort. And what I realized there was that sometimes something like this will happen that I want to maybe I maybe let's say wanted to bring this guy to its correct position, and there was some element on this position which got to its correct position. So I saved one operation there. Something like this happened a few times. And then what I realized was there would be some sort of a chain. Like people go to okay. There is only one chain. Now that's why we are not able to notice this. Yeah, the example was bad. Let's pick up an example like 0 to 1. One should go here, so 3 should come here. Let's say 4 is here, and yep. If let's say there is something like this, you would like to bring 0 at the first position, then you would like to bring 1 at the first position, and you would like to bring 2 at the 2 at its correct position. So we'll have the array 0, 1, 2, 3, 4, right? You swapped these two, so 0 came here, 4 came here. You swapped these two, so 1 came here, and 3 came here, and 0 is also on the correct position. Then you swapped the 2 and 4, like here was 4 and here was 2. So 2 came on the correct position and 4 came on the correct position. So what happened here is for the people 3 and for the people like for the people 3 and 4, I had used an operation to make this guy come on the correct position, but I got another guy on its correct position. Similarly, I wanted to make 2 come on its correct position, but 4 also got to its correct position. I was just lucky to get this. है ना? So I tried to think, can I find out how to maximize this luck factor, or would it be constant? And if it would be constant, then how many elements will there be who will get to their correct positions luckily? Right. So while thinking a little bit, I realized one thing. If I try to take 4 like 0 to its correct position, obviously 4 would eventually um like since as I have to get 0 to the correct position, similarly I want to get 4 to its correct position also. Then there is 2, so I want to get 2 to its correct position as well. है ना? And you are actually gonna be having a cycle in this way. Every guy has exactly one place there where he wants to go. So eventually there must be a cycle. And if there is a cycle of 3 size, I will make only 2 swaps. One swap for getting this guy on its correct position, one swap for getting this guy on its correct position. For the last guy, it will automatically get to its correct position without me being uh, like uh, without me having the requirement to apply one extra operation on that guy. Guys, please tell me if it is making some sense or not. I can just repeat everything for the B problem because I think I just went off board at one place. Do you mean we can sort this vector? Okay, everything till this point was good. It is sure to be lead code in Java, so HC most people C++. Java. I don't think it is difficult to do lead code CP in Java. but mostly people use C++, so it's better. Like you will have a larger community support. If I want to solve a problem, I will find out way more solutions in C++ in comparison to Java. Okay, how cycle idea came? Yeah, I will just repeat everything from starting for the B problem. Sometimes this happens because um, I did not have a lot of time to think about the complete way in which I will discuss this. And sometimes during the explanation, I realized that things that were looking way too natural for me might not look natural for the viewers. So I try to explain it in a little different way from how I had thought, and I just realized that I messed up. So let's have a 2 minute break and then I will continue. Okay, so let's begin. The B problem says that we have been given an integer array nums with n integers. All of these elements will be positive and distinct. Okay. And we are being told that we need to sort the array in increasing order based on the sum of digits of each number. If two numbers have sum of digits, same digits, and then the smaller number appears first in the sorted order. So if you have array like um, 10, 11, 9, 4, then in that case, you want to sort the elements in a way that the people having the smaller sum of digits should come here, and the people with the larger sum of digits should come towards the end of the array. In case if there are elements with same sum of digits, let's say if there are elements in the array with same sum of digits, then the smaller guy should come first and then the larger guy should come. So here the sorted array would look something like this. Um, 10 because the sum of digits is only 1. Then these people have the same sum of digits. Like these people have the same sum of digits. So 2 will come first because it is the smaller number, then 11, then 4, then 9. This is how the sorted array will look like. Now we are being asked what is the minimum number of operations um, in which you can, or minimum number of swaps in which you can sort this array, transform this array into this array. Again, in one operation or in one swap, you can just choose any two people and then swap them. Okay, so this is the problem. Now the first task for us is we don't even know where we would like to bring these people, right? Or actually, you can find it in somewhere. You can do something like this. For every element, just find out the sum of digits. And now the guy which is having the smallest sum of digits, just try to bring that guy to the front and keep on doing it until you sort the complete array. You can do something like this. So first of all, let's um I- let's just go in the most intuitive way. You would like to find out uh how the sorted array looks like, so that your thought process or the way for approaching the problem will become a lot simpler. Like this thing is gonna be helpful in generally the more difficult problems that do the most obvious things first. Like for this array, since you know you want to sort it, but you don't know how the sorted array will look like, why don't we just think about this first? That how will the sorted array look like? Hana, you don't really necessarily have to code this. Right now, we are just thinking in a way how you would like to approach the problem. So you would like to find out the sorted array first. How would it look? And yeah, so for finding the sorted array, on paper, it's simple. Just find out the sum of digits for every number and then sort it as we have done. For the code part, if you would have to do it, you will just say you have two things, sum of digits, num_sci, because this is the first parameter that you will have on the basis of which you want to decide which guy should come on the first place and which guy should come on the last place. And the next thing you have is num_sci itself. So if you create a list of or an array of this type for every I from 0 to n and then sort it, then do you guys agree that we will eventually get the or sorted order, like sorted array? If the array look like the example test case 18, 43, 34, and 16, and we just say that create a list of sum of digits of nums and nums, which would look like 9, 18, 7, 43, 7, 34, and 7, 16. Um, then we can just sort this thing. So the people having the first guy equal will have the smaller guy come first. So the array will look like 7, 16, 7, 34, 7, 43, and 9, 18. Right. The array will look like this. And after, like once you know about the sorted array, in general, we did not really care about this guy. In the sorted array, we had only this guy, which we cared about. You know, the array after sorting should have looked like 16, 34, 43, and 18. So we only have something to do with these people. So you can just um, consider that we have got the sorted array like this now, right? So basically now we know for every guy in the original array, we know where we want this guy to go eventually, right? This is one way in which you would have thought. Another way that we discussed here, uh, if you directly got the idea that for sorting, what if I just find out the guy with the smallest sum of digits and the smallest value and bring it to the front and then do the same thing for the second guy, for the third guy, fourth guy, and so on. You could have got this kind of idea as well. And um, in the explanation, I don't think I can cover up all these ideas and what ideas, like what could be the thought process for this kind of idea and so on. Actually, this will also work if you had this idea, but um, if I prove everything, then the explanation will go too lengthy. So I will tell you about the way in which I had been approaching. So I had got this kind of an idea. As soon as I knew that I have to sort the array and I can do the sort operation, like I can do the swap operations. So from the original array, I tried to think about how the sorted array will look like. Once I knew how it would look like, I just thought that, hey, in the problem, I can create this sorted array. So if I have something like 18, 43, 34, and 16 that I want to convert into something like 16, 34, 43, and 18. The idea was you can just consider these two arrays as 0, 1, 2, 3, and this 18 is coming here, so 3, 43 is coming here, 2, 34 is here, and 16 is here. Basically, the number of operations required to transform this array into this array would be equal to the number of operations required to transform this array into this array, right? Because it is pretty much like for every guy, I just gave a key, a unique key. Maybe I could have used something like ABCD also if I had done ABCD. Uh, if I had mapped 18 with A, then I could have said something like this that I have ABCD that I want to convert into DCBA. The benefit of mapping like this is if I just map these numbers with these digits, then for the resultant array that we have, since it is having elements not really in the sorted order or something, I can give some mapping for every element to make sure that the um, resultant array that I would want to have is gonna be a sorted array. है ना? That makes the problem a little simpler to think about, right? This makes the problem a little simpler to think about. Just imagine if the array was something different. Let's say if it was 18, 16, 34, and 43. I have to transform it into something like this. This, to me, at least to me, it looks a little less easy to think here. Whereas if I think about this problem in a way that for the final array that we would like to have, the sorted array, just give mapping, some mapping for every element, like consider the 16 as 0, 34 as 1, 43 as 2, and 18 as 3. Then my this array will look like 3, 0, 1, 2. In my opinion, thinking about how to sort this array would be a lot simpler, right? And right now we have a type of operation in which you will just choose two elements I and j, and you will just swap ai and aj, right? So for this kind of operation as well, sorting this array into this looks simpler. So guys, are you able to get my idea? Like uh, the reason we did this kind of simplification, mapping every element with some elements from 0 to n minus 1. I know this might, the re-explanation for B might be looking even worse till this point, because when I'm explaining my idea to someone, if I'm explaining it to it for the first time, for the real motive of explanation, it is gonna be better. Right now, it is looking a little fake to me since I'm repeating it for the second time. How you got to know list approach from question? List approach. Okay, are you talking about this list idea? This list idea is just for sorting the array. You want to sort the array in a way that the people having smaller sum of digits comes on the left and the people having larger sum of digits comes on the right. Right. You want this kind of thing. So one possible way is to just write your custom comparator to decide which guy should come on the left and which guy should come on the right. Another way, which I believe a lot of people would be used to doing, is just uh, create a new array with multiple um, elements at every index, maybe like a pair or a tuple or something. Like in this case, I created a pair. The first guy, like while sorting, you want the smaller sum of digits to come on the left and the larger ones to come on the right. So that is why this is the first element I'm having in the pair. Nextly, for the case of ties, as a tiebreaker, you will say the smaller guy should come on the left and the larger guy should come on the right. So that is why I'm putting up nums of I at this position, at the second position. So if I create this kind of a new array and then sort it, then the people having same value of sum of digits will come together from left to right in the sorted order. And then the second element would be chosen as the tiebreaker. In case if you had something like you wanted the larger guy to come first in case of a tie, then you could have stored either maybe something like minus of nums of I, and then you would know like uh, in the final array would have something like minus 43 here, minus 34, then minus 16 here, and minus 18. Then obviously at the end you can just multiply every number with -1 to fix it again. And custom comparator is obviously the best thing you can do almost all the time. So if you know about custom comparators, just use it. If you don't know about it, go to Geeks for Geeks and learn about it so that you can use it in future. Once did not get Fury, can you please point out a little bit like which part you want me to repeat? And by the way, the problem is not done yet. Now we are having one important thing that we want to do, that is find out the minimum number of operations required to sort this array. We have got a way simpler problem for us now. Now we want to find out how to sort it. Now, so we will talk about this. Just waiting for Fury's reply once. Yeah, I got your approach. I'm asking generally when you should consider, when should we consider from problem like list approach. To be honest, whenever I want to sort an array, at that position I think about creating a new array. By the way, by this word list, I'm not talking about the list data structure. I'm talking about array only. Right now, I'm talking about something like a vector of pair of ints. Yes, sir. After mapping the values, it will be question becomes minimum swaps required to sort the array. Yeah, standard problem. Okay, so for doing this task, when I got the problem like this for the first time, I don't know how many times I said this. Um, like the idea was something like, oh yeah, there is another way. You might have actually heard about this also, that selection sort, the algorithm selection sort has the minimum number of swaps required for sorting an array. You guys might have heard about this. In case if you never got to know about this, then congratulations, you got to know about this in this video. So we can use this information. Selection sort will have the minimum number of operations. What we do in selection sort is just for the first position, find out the smallest element here. For the second position, find out the smallest element in this range. For the third position, find out the smallest element here, and then find out the smallest element here. Every time, whenever you find out the smallest element, you just make a swap. Find out the smallest element, make a swap, and so on, right? You do it in this way. So if you apply that approach, you will have the minimum number of swaps. Right now, if you do the standard selection sort, if you apply the uh, normal selection sort technique, you will have the go of n square time complexity, which is going to give you a TLE. But you can optimize it. Instead of running a whole for loop for this whole place, you can store all of the elements and their indices inside a set. You can have something like a set of pair of int comment, where the first element of the pair would be the nums of I, or not nums of I, but this new array that we have created. Let's call this new array as array B. So the element bi and guy I, and I can store something like this to find out the smallest element and its index. All the bi are unique, so there will be exactly one smallest element. So exactly one index would be there. And then you can make swaps, and this is one way in which you would be able to solve the problem in minimum number of operations here. Another way Um, Actually, it's related to this approach only. Like the way in which I had got to know what was similar to this. I was trying to bring the smallest elements to the first position again and again. And then I realized something, that in the array, since for every position, there is exactly one position where that guy wants to go. You know, if you have converted your array into elements from 0 to n minus 1, then an element with the value ai, um, like since every element from 0 to n minus 1 is coming exactly once. So do you guys agree that if you have element 4 at the second index or the index 1, then the optimal place for this guy 4 is actually the index 4, because we will have every person from 0 to 3 on the left of 4 and every person from 5 to n minus 1 on the right of 4 in the sorted array. So 4 must be the place where this 4 guy wants to go, right? So my idea was, what if I want to take it to 4, position 4? Then the guy on this position, it will come here, and also this guy would also want to go to its correct position. Let's say it wants to go to this position. So it's basically like I went to this position. Now the new guy that is being affected, who wants to get to its correct position, is this guy, which will go to this position. Now, whatever guy is present on this index would like to go to its correct position. And eventually you will find some element which wants to reach to this position itself, the starting position, like the position where you had the 4 guy, right? There will be a chain. You can call it a chain or a cycle. You know, so it might be a little difficult to visualize. In case if you feel it difficult, then just go with the previous approach. The problem can be solved with this much only. Right now, what I'm telling you is um, the way in which I had got the idea, and I think it's something you should know. For like in general way, you can say, if you have n elements and every element is pointing to some place, maybe this is the place where it wants to go, or it can be a different problem, but this guy is pointing to some place and that guy is pointing to some place, that guy is pointing to some place. Every element is pointing to exactly one place. So eventually you will come back to the current guy. You will have a cycle for sure. One way to prove this can be by using graphs. You can consider these n elements as n nodes, and every node is having exactly one outer degree. So there must be at least one cycle. And for every component, you will have exactly one cycle. If you think about this problem in terms of graphs. And the main thing, the main uh, useful part here is, let's say on the index 0, you have on the index 1, you have the guy 4. On the index 4, you have the guy 0. And on the index 0, you have the guy 1. Then for correcting these three people, making sure that these three people comes up on their correct positions, you need only two swaps. Because once you fix this guy and this guy, the last guy will have only one position where it would be. That would be its correct position. So for a cycle of x size, you have to use x minus 1 operations. Let me give you another reminder. This approach might look complicated to some people. In that case, you can just use the previous approach where we were using the fact that selection sort has the minimum number of swaps required for sorting the array. Um, and the number of swaps required there would be exactly equal to the number of swaps in this approach, by the way. And we can just optimize selection sort by using set of pair of integers instead of running a whole for loop every time. And I'm discussing this part only because I feel this is something good to know about. Even if you understand it partially, it might be beneficial for you in future. And the more you think about this approach on your own, the better it would be for you. So this is one thing that we have realized. You will definitely have cycles. Um, and it is possible that you might even have a one cycle having all of the elements of the array. It is possible, like you might have something like this for for an array of 4 size, an array like 2 3 4 1, not 2 3 4 1, but 1 2 3 0 in zero based indexing. 0 wants to go here, 1 wants to go here, 2 wants to go here, 3 wants to go here. So you will have a cycle, just one cycle, or you might have multiple cycles, or you might have even something like 0 1 2 3 having 4 cycles. You know, in this case, every cycle is having just one guy, and 0 operations are required to fix that cycle. So the total number of operations required would be nothing but the sum of total number of, like the sum of x minus 1 for all cycles where x is the size of the cycle, or basically size of cycle minus 1 for all the cycles, right? You know that for all the cycles, the total number of elements over all the cycles would be nothing but n, right? At the end of the day, this thing would be equal to n. Overall total number of elements will be just n. So the overall idea becomes n minus the number of cycles. One way to say this problem would be like this. Another way is like this only. That go over the array from left to right for every element, find out its cycle, and mark all the indices true, so that when you go to this index or this index, you would know that, hey, we have already considered this cycle. We can do something like this. Nextly, whenever you find a cycle, if you, let's say, found 3 people, then increment 2 to the answer. Or another thing you can do is just increment and like initialize answer with n initially, and find out the number of cycles. Whenever you get a cycle, visit all the people and decrement the answer. You can just use your creativity here. So guys, is it making more sense now? Like, is the problem actually clear this time? How do you map with original sort order logically? Okay, nice question. One possible way for this is create a map. Create a map. You have already obtained this array, right? Like from the original array, you created a new array, then sorted it, and eventually you have got this array. Or if you want, you can even create this array, the sorted order. Then just iterate over it. You can have a map. When you get to this guy, in the map, just store 16 0 because the index is like this. For 34, just store 34 should go to the index 1, 43 should go to the index 2, and 18 should go to the index 3. You can do it in this way. This is one possible way. Um, yep, I think one doubt is clear. That's the next thing. Similar problem is there in CF to find minimum operations too. Minimum operations and permutations. Okay, yeah, that might be true. You made first approach vector thing in sort first vector and then sort and compare with the old. How many elements changed from its position? Is it possible to answer like this? No, no, no. It has nothing to do with how many people changed. You might have an array like 1 0 3 2 5 4 7 6. So here all the 8 people are on their incorrect positions, but the number of swap operations you need are only 4. So by just judging the number of people on the incorrect positions, you will not be able to find out what should be the answer. You might require 7 operations, you might require 4 operations, depending upon how the array is there. Can you dry run the code so that we can get more easily? Uh, yes, I can dry run. And can you explain the set approach once again? I'm stuck in that. Okay, I will explain the set approach. How to find cycles in our case? For cycles, all you need to do is just like iterate from left to right for every index, just um, run a while loop. Like let's say j is initially 0, then the guy here was 1, so you will go to the index 1, you got the guy 4, so set j equal to 4, then go here, you found 0, set j equal to 0. Eventually you will reach a place which you have already reached earlier. Wherever you visit, you can just mark it true, like you can just mark it visited. So whenever you reach a visited place, you know that you have traversed the complete cycle. So that's it. And when you do this thing for every element, um, the number of times you will travel like this would be just the number of cycles you have. That's it. Okay, talking about the set approach, you were asking for this. See, in the selection sort, if you had something like 3012, or let's say 3102, what would you have done? You would have iterated over this complete array to find out the smallest guy. You found the 0. You will keep track of this index of the smallest guy, and then you will swap these two people. Now, you will get your array 0132 now. Now for the guy 1, you will iterate over this whole range to find out the smallest guy and then swap the index with this guy in case if the index is different from whatever element you have here. Then you will check for this guy, iterate over this range, for this guy, iterate over this range, and so on. Right. So what I'm saying is, if you iterate with this big of n size for loop every time, then you will get a TLE because your time complexity will become big of n square. So a better thing you can do is, um, instead of iterating over this again and again, keep track, like keep a set in which you have already inserted the elements with their indices. Like 3 is at the index 0, 1 is at the index 1, 0 is at the index 2, and this guy 2 is at the index 3. Right. Now, if you store it in this way, um, then for the first position, you just know, like in the set of obviously things would be um in like would be there in the sorted order. So in the set, things would look like this: 0, 2, 1, 1, 2, 3, and 3, 2, 3, 0. Right. So you know that the smallest guy is at the index 2. So you will make a swap between these two positions. And remember one thing, when you make a swap between these two positions, um, now this 3 will no longer be present at the index 0. So what you can do is, first step is find out this index. The second step is remove this guy and this guy, like the people on the index 0 and 2 from the set. We can remove it easily because you know the people who are present on those indices. Once you have removed these two, make a swap, and now you don't really need to insert this guy anymore. You don't really need to insert a 0 because you have, you know, that this much is sorted. Now for this remaining array, you know that at this position you have got a 3 now. So you will just insert 3 comma 2 now in the array. Sorry, not array, but in the set. So your set will now look like 1 comma 1, 2 comma 3, and 3 comma 2. And I believe this is pretty much doable from this point. Now question 3. Yeah, so shall we move on to the question 3? I will just show you my code. In my code, I have included a good way of implementation for the way of finding the orders. So I will explain that one also once. Okay. There is just one thing left for implementation. First of all, you can always code your problem with this logic. I will actually code it in front of you if you want for this. Nextly, um, there is a better way of implementation in my opinion, like especially for this part of finding this stuff, what you can do is, um, you can create a vector of integers with name, let's say ord or order or something. Um, and then insert values in that array from 0 to n minus 1. Either you can run a for loop or you can just use the iota function for this, and then sort them in the way with the conditions that you wanted to have. So what will happen in this case is you will directly get this array. Not like this, but you will directly get this array, this in the ORD function. Now, um, in case if you are able to understand this code by looking at my code, I've written it very clearly. If you are able to understand it, then that's good. In case if you're not able to understand it, then just skip it for now and just go on with the normal approach that I discussed here. Um, it should not be difficult to understand, and uh, I feel that it is something you don't really need someone to explain to you. Either you are able to understand it yourself or you need to give yourself more time. Nextly, this is the code part for finding the cycles. I'm having answer equal to n initially. I'm having a for loop from 0 to n. For every element, I'm checking whether it is visited or not, because if it is visited, it means that it has been a part of a cycle already. Otherwise, it would not be visited. And in that case, I will run a while loop, initializing j with I, and then go on to the, like, this same idea that the same idea that we had in this case, like uh, go from this zero guy to this one, then from this place to this place, this place to this place. Eventually you will reach the initial index, that is I, that would already be visited. So everything would be cool. And yeah, one possible mistake that you can make here is, um, if you say j equal to odd of j first and then you write the visit line, then like it won't cause any trouble for this specific problem, but it is not a good way, because um, what will happen in this case is you will move on from this guy to this guy and you will mark this instead of marking this and then moving on. So you might end up making a mistake in some more complicated problem someday. That's why I do recommend, do whatever you wanted to do with the current index first and then move on to the next index. And I'm reducing my answer every time because I have found a cycle, and then I'm returning the answer. So is it clear enough? And for the other approach that we had, what we would have done is we would have created something like this. Yeah. Um, yeah. In the set, you can simply insert um, ORD I and I. And then for every position from 0 to n, you want to find out the smallest guy. And the smallest guy is actually having two things. Um, Smallest value and the smallest index of the smallest value. Right. You will get these two things. And then what you would do is remove the elements from the set, remove this guy and this guy from the set, for which uh, you know the value of the small, like, yep, exactly. This smallest is gonna be just this. It is the first guy, that is st.begin. You know, one of the people that we want to remove is gonna be the first guy, because you would be swapping this guy to come at the first position. Next, the other guy would want to remove is the person who is present at the index 2. Uh, no, the person who is present on the current index. The person who is present on the current index. So you would like to erase um, st erase odd of I and I. No, right now I'm using the odd array. Like the array is named as odd. You can do whatever the name is. Let's say the name is B or something. Um, and nextly you would like to insert this 3 comma 2 thing. So this 2 is the index of the smallest element that we found, and 3 is the value of the current guy. So you would eventually like to insert the current guy and the smallest value index. Your code should look something like this, and obviously you can make a swap if you want. And yeah, I think you should make a swap. Swap odd of I with odd of smallest value idx. Now, in general, I would recommend to have this line. Yeah, eventually, yeah, okay, yeah, even in general, I would like to recommend you something like this. Remove stuff from the set, make the swap, and then insert the new guy. So that's how your code would look like in general. I'm not understanding odd line code. Can you suggest how to understand? This is something you just have to do yourself. Like, nobody taught me anything that I've discussed in this problem. Like for both of the ways, neither the way related to using the set in this way or that. And all of that comes from creativity. Nextly, even for finding the cycles and all, and even for the part of understanding that odd thing. So, uh, my experience says that this is something that should not be taught. Instead, you should just put up efforts by yourself to understand it. It's simple. Like you are creating an ordered array, having elements from 0 to n minus 1 here. Then you are sorting in a way that the guy who comes on odd 0, um, like if the array looked like 2 1 0 or maybe 2 4 0, then the order guy for this will look like 1 2 0. This guy should be at the 0th position, so it would be 0. This guy should be at the second position, so it would, here it would be 2. And this guy should be at the first position, so it would be 1 here. Yeah, let's move on to the next problem. Some people are also willing for this to happen. And okay, the third problem, grid teleportation. Okay, let's do it in one after a 1 minute break so that I can give rest to my throat. Okay, I'm back. Can I get your code? What you explained in class? Yeah, I will after after the PCD, I will submit with the other approach as well, and will give you the code. Use custom comparator for sorting. Yes, that's good. Q3 is variation of the extra. We have to keep track of characters A to Z and move directly to the cells that we have. Yep, exactly. By the way, you don't need to use the extra. You can use 01 BFS. Um, so the problem says that we have been given a 2D character grid of size m into n, represented by an array of strings. Matrix ij represents the cell at the intersection of ith row and jth column, and blah blah blah. Dot represents an empty cell. Hashtag represents an obstacle, and an uppercase letter A to Z represents a teleportation portal. You start at the top left from 0, 0, and your goal is to reach at the bottom, that is the m-1 cell. We can move from current cell to any adjacent cell, up, down, left, right, as long as the destination cell is within the grid bounds and not an obstacle. If you step on a cell containing a portal letter and you have not used that portal letter before, you may instantly teleport to any cell in the grid with the same letter. This teleportation does not count as a move, but each portal letter can be used at most once during your journey. Return the minimum number of moves required to reach the bottom right cell. If it is not possible to reach the bottom right, or basically the destination, we have to return -1 in that case. Um, in general, I just delete it because this is all scribbling. If you want to read it, you can just pause the video and read it. In general, if I teach something for which the notes are good to have, then we do share the notes, and that generally happens for TLE classes, like the theory classes mainly. The notes are shared, and for problem solving classes also we share the notes, but I don't think it's required there. Anyways, let's come to the C problem. Here we are being given um, a matrix of m into n size, but for the explanation purpose, I will always say n is the number of rows and m is the number of columns. Um, this is just due to my preference, and it does not really matter much. And I have used this same thing in the code. That is why for the explanation, I'm not using m and n. Instead, I'm using n and m. So the problem tells that, hey, this is a grid. Every cell will either have a dot, which represents that the cell is empty, or it might have a hashtag that represents that hashtag is like this one. Yeah, it might have a hashtag that represents that this cell has an obstacle, or it might have something like A, B, A, C, whatever. It might have some characters which represents some portals on these cells. So if you have a portal on this cell and on this cell with the same letter, that is A in this case, then you can move from this cell to this cell instantly without any cost. We are being told that for all characters from A to Z, we can use those portals at most once. You have to start from this point, that is, this is the starting point, and you have to reach to this bottom right cell, that is the ending point. And minimum number of operations, or actually minimum time. I think they use the word time there or whatever. Minimum moves. Yeah. So you have to reach there in minimum number of moves. And by the way, if you move from this guy to this guy, it is not counted as a move. Like, you can use the teleportation without increasing the number of moves. So for now, let's take an example. If you have a grid like this, here is a character A, here is character A, and all of these cells are um, like this. So you can just you want to move from here to here. The simplest way is use the teleportation here to reach to this place, and then use one move here to reach to the end point. Right. Use this teleportation, then one move, second move, and in two ways you are able to reach to the destination here. This is the first sample test case that we had. Another sample test case that we had is this, and they have actually shown a very good animation here on how you can cover this whole area. Okay, so is the problem clear to everyone? I hope it would be. Um, Sorry to hear about this. Kshitij, please just uh, pardon me for the B problem, and for the C problem, I will try my best to keep it good. For the B problem, I had actually uh, failed to tell me about my thought process, and then it just got way too messy. Like the thing that was looking way too natural to me during the explanation, I felt that hey, this might not look natural to people, and I just got confused on how to teach for that thing. Um, Anyways, let's talk about the third problem for now. Okay, so for now, this is how we could have done this first sample test case. Now, in case if you did not have uh, these teleporters, do you guys agree that a simple BFS could have solved the problem? Right. This is the first prerequisite I want from you. You guys should know at least this much, that in case if you did not have um these teleporters, then this is a very standard problem for BFS. Right. If you learn about BFS, you will get this problem for sure. Nextly, um, there is a cool idea that I will tell you about. Um, in case if you have never seen this kind of thing before, then it might not look very intuitive to you, but it would be understandable easily. The thing is that if I have Oh, I'm sorry, Wi-Fi got out, and I got to know about it just now. Can you guys tell me till which point was I audible and visible? Was I audible till this point at least when I talked about BFS? That in case if there were no portals, then BFS would have worked. Can't hear you. It's frozen. Is it like am I still not visible properly? Okay, I'm visible. Nice. Okay. See, let me just repeat it from the scratch again. In the C problem, I discussed the problem statement first that we are being given a matrix of size n into m. Um, and we want to go from the top left to the bottom right. There will be some obstacles in the way. There will be some empty cells denoted by the dots, and there will be some portals. You can teleport from one portal to another portal such that like in only the condition where the portal from where you are moving is having the same character to the portal where you are moving. Like from any A, I can move to any A, whether this is this A or if there is an A here, I can move here also, and so on. But I can't move from A to B or A to C. Okay? And when I move from any cell to left or left, right, up or down, I will use one number of move in that scenario. But when I move from a portal to another portal, in that case, I will not have any cost. Like I will have a zero cost for the teleportation. So for this problem, we had discussed the sample test case. Like if you had this sample test case, you can just move from this initial cell to this portal, like this cell by using the portal, and then use two moves to get to the bottom right. Then we did discuss about, I don't know what is this ABC doing here, but we did discuss about a few obvious things. First of all, in case if the problem did not have any portals, I could have used a simple BFS to solve it. Now, in case if the problem had portals, okay, let's talk about the third observation first for more clarity. Another thing is, even if like in the problem, they said that I can use the portal at most once, but even if I could use it more than once, is it any time better than not using it? Like, let's say if I go from this portal to this portal, then I travel from this place to some other portal of A, and then I apply an operation. Like I teleport from here to here. Is it any better for me than directly going from here to here? No. So even if I could apply the operation more than once, it is always best to just apply one operation. You know? Because if I'm moving from here to here, then at some other point I move from some other portal of A to some portal of A, then I can just save all of this mess where I would be using moves from moving from left to right and so on. I can use like I can just save all of that by moving directly from this place to this place. So in a nutshell, the condition which said that I can use a portal at most once, even if it was not there in the problem, the answer will still be the same because ideally I will never use it more than once. Okay, so I can just forget about this condition for now. Nextly, the thing that I wanted to discuss was that even if there are portals, like if there were no portals, I could use BFS. But even if there are portals, I can just consider these cells as the adjacent nodes, right? I can just consider as if these nodes are connected by some edge, right? So guys, are you able to see it? Like in this case, the time complexity would be very bad because you will have around n square in the worst case. You will have n into m number of connections for every node. You know, in this case, for every node, it is having this many neighbors. And in total, there are n into m nodes. So you have got your time complexity as n square into m square. So guys, do you agree with me so far? Are you able to understand these 3 points? By the way, all these three of them are pretty common. Like you can see this kind of stuff in a lot of problems. Whenever you see a whenever you see a problem in which you want to find out minimum number of moves for moving from some place to some other place, try to figure out what are the extra things which if were not present you could have used a BFS. You know, use like try to think about this thing in problems. Whatever extra part that you're having, try to think whether it will affect your BFS or not. And whatever different operations you have, always try to analyze them. Like in this case, we have the operation of moving from some place to some other place. है ना? So, and we are not allowed to do it more than once. So, is it actually affecting my answer? If yes, then in which conditions I would have tried to see, in which scenarios this is affecting, and which scenarios it is not affecting. Try to focus on these things, and with experience, you will know which um, things you should think about. Like in future, now I believe whenever you see something like this, portals connecting to each other, you will have this idea in your mind that hey, I can just consider all of them as edges between nodes, right? I can just consider all of these cells as different nodes and the neighbors as connected via some edges, and the nodes that are connected via some portals are also connected with each other with weighted edges having weight 0. Like neighbors will have a weight of 1, but cells having the same letter will have a distance of 0, like the weight of 0 for the edge. Again, next thing is right now in our solution so far, we can actually solve the problem. The only trouble for us is that, uh, okay, there are two troublesome things for us. First of all, we can have edges of two weights, that is 1 and 0. And this is one troublesome thing. In BFS, we generally have only edges with weight 1, or all edges should have the same weight. So a solution for this thing is, if you ever have a graph in which there will can be weighted edges, but every edge will either have a weight 0 or 1, then and you could have solved the problem if the weights were just 1 with BFS, then there is something known as 0 1 BFS, which is basically a simple modification in BFS, and it does work for weighted edges where the edges are of weight 0 or 1. And in case if you don't know about BFS, 0 1 BFS, one thing you can do is just search about this. I think it is available on CP algorithms. And if you are right now not in mood of searching about new stuff, you can simply use Dijkstra also. The only problem with Dijkstra is it will have a log n component added. है ना? It will have something like big O of n log n time complexity, whereas 0 1 BFS will have only big O of n time complexity. So better thing to do is this, but you can still use Dijkstra, I think, if the time complexity does not go too high. Next trouble here is we are having too many edges. You know, we are having too many edges. So fourth thing was 0 1 BFS for dealing with the 0 1 edges. The fifth thing is we are having too many edges. And this is actually a very interesting thing to deal with. If you have heard about um, what do we say? DSU. If you have learned about DSU, then probably you should know about this. What we can do is, like for all these nodes that are having A written on them, instead of connecting these nodes with all the other nodes and making a complete graph of these, what you can do is create a dummy node with, let's say, name A, and connect that node with all of these cells. You can do it in this way. Create a dummy node A and connect that guy with all of these people. So what will happen is instead of moving directly from here to here, what you will do is you will move from here to here with a cost of 0 and from here to here with a cost of 0. This is how our solution will look like in this case. We have characters from A to Z, so you can have 26 dummy nodes. है ना? I'm calling them as dummy nodes because these nodes were not ideally present and they don't really have much of a significance other than making sure that um, like if you had something like this, 5 nodes connected to 5 of these nodes, and actually these nodes connected to each other also. Or maybe let's say if you had something like this, and we are having just way too many edges in this case. And I'm not even drawing all of the edges and still it's really cluttered. है ना? We are pretty much converting this kind of thing into something like this. Add a dummy node in the way, in the middle. You just need to verify this one thing once, whether all of them being connected together or all of them being connected via a dummy node. Will this thing actually cause some trouble to you? Like, will it change the logic of how things should happen and how not? Like, if the edges actually had some significance about from which node to which node it is going on, in that case, you would not be able to add a dummy node like this. But right now, the edges does not have anything to do with from where you are coming to where you are going. All it has to do is what is the minimum possible cost to reach till this place, and then you are going to be adding just one step here or actually 0 steps here. You will just update that, hey, I can reach here in this cost and so on. Basically, just I would recommend you to try to think about um, this for 5 minutes or so, whether having a dummy node will change the logic at all or not. In our case, it will not actually, right? And by the way, I've created these directed edges just for showing you how adding a dummy node is making things a lot better. Here I will have a lot of edges. Here I will have around 25 edges, whereas now I am having only 10 edges. And as the number of nodes increase, this thing will grow exponentially. For n nodes, you will have n square edges here, whereas for n nodes here, you will have 2n edges, like n nodes here and n nodes here. So you are having 2n edges. So are you guys able to get the point? Yes or no? This is actually a very interesting idea in my opinion. When I got to know about this kind of an idea for the first time, I was not able to think about it on my own. But after reading the editorial for a code forces problem, I was really happy to learn about something like this. And if you see, this is actually similar to what we do in DSU. In DSU as well, we are actually adding, let's say you are having n people for which you want to maintain which people are in which group and so on. We create a DSU in which we are actually having n dummy nodes. है In general, we are having these dummy nodes. We create an extra nodes for just keeping track of which people are connected to which people and so on. So here a graph like this one having 5 nodes all connected to each other or something uh, will just look like this. 5 nodes all connected to just one dummy node. And in this way, all 5 of these are connected to each other with just 5 edges added this way instead of n nc2 number of edges. है ना? And by the way, let's say if the weights of all these edges were 1. Right now in our problem, the weights are just 0, so it's not a problem for us at all. But let's say if the weights were 1, 1, 1 for all the edges here, if you are applying this kind of a idea of adding a dummy node in a problem where you have edges all having weights 1. So you can do something like um, add directed edges here, where in the directed edges, the cost of moving from this point to this point is, let's say, 1, and the cost of moving from the dummy node to the current node is 0. You can add this kind of a logic for all the nodes. So overall, every node here would be connected to all the other nodes with a cost of 1 only. Or maybe do it the other way as you wish. I don't know which one is, like, I don't know what is the difference in both of these, but I once saw a problem in which one of these ways was working and another way, like this one, was not working. And we could not really figure out the difference. Maybe there was some other mistake due to which it was feeling like that. Hello. Hello. Okay, yes, only till first point. Okay, guys, would you like to give me some live feedback for the C problem explanation so far? Is it looking good so far? Do you think that the problem is looking a lot doable now? We are pretty much done. We are pretty much done. And I have told you about a generic solution, not just for this problem, but it can work for different cases as well. Like if the teleportation cost was also 1, then you could have done something like this for making sure that your solution works there. And there is one more thing that I would like to discuss. In our problem, since the cost for moving from here to here is always just 0, and we know that we will, like, this node should be used exactly once. If there are like multiple places where the portal is coming, you will move from, like, whichever portal you are able to visit first. Obviously this is the only time, like, let's say there is a portal here, 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 and here, and I can reach this portal with the minimum distance. So obviously I will never move from any of these portals to some other portal via that portal operation, because if I have to move from here to here, a better thing to do would have been to move from here to here, right? So one thing I can do is I can just limit this thing also, that I will have to use this portal operation exactly once, never more than that would be required. So you can even avoid the dummy node wala part. You can just say, whenever you will find out a portal like the character A for the first time, only for the first time, then you will um, just consider the edges from this node to all of these other portals. But for any other node, you will not consider it having an edge from here to all the other nodes. Like you can do it in this way also. And this is how I have implemented it. Okay, this teleportation does not count a move, but each portal letter can be used as different at most once. I had talked about this idea of the condition that a portal can be used at most once. That even if you could use the portal more than once, you will never use it. You know? So if you are writing an algorithm to find out the answer, or basically the minimum possible answer, in that case, you're pretty sure that if there is a possible answer in which you are using portals more than once, then you will definitely have an answer in which you are using the portal at most once also. Because if I can do something like this, use portal A to move here, then move reach this place and then use this portal, then I could have directly done this. And if I had to go to this place, I could have directly moved to this place. So for all the other ways in which I could have basically moved here and then try to apply the operation, that will never happen. Like in our case, if you're actually considering a dummy node, you see, this dummy node would be visited at most once only, no? As you have all the other nodes that would be visited exactly once, similar thing will happen with the dummy node. It would also be visited only once. It will not be visited after it has already been visited once. Getting TLE For the third problem, use PQ and what? By the way, I also got TLE for the third problem. I'm not sure of what was the problem with it. Time complexity looked fine, but anyways, here is the other approach with which I've coded it later on. What we have done here is, since like for any portal, let's say a portal is present here, and there are more occurrences of the portal. Before thinking about the dummy node, we had considered that for all of these nodes, we can just consider that it has so many neighbors, है ना? But since this node would have the minimum distance from the starting point, obviously it will provide the minimum possible distance to reach the other nodes. So in that case, I will not look out for from these nodes to visit the other nodes through the same portal. Basically, I will use every portal at most once to optimize my solution, like without even using the dummy node. Is it making some sense? If it is making sense, that's great. Otherwise, you can just use the dummy node stuff. Can you please explain how these teleportation portal point is used? See, the thing is, you will start from the top left. Eventually, you will reach some nodes. Like let's say you reached a cell where there is a letter A written. So now either you can move to any other cell as you could have done at any other cell before also, or you can just move on to any cell which is having the same character. Like other than the four neighbors, you can move on to these people also. And when you move to these people, you would not even have a cost involved. So we can directly move on to the other portals or the other cells with the same letter portal. And my idea is, if you can reach to this portal with a cost of 10, this portal with a cost of 12, and this portal with a cost of 11, है ना? And let's say there is another portal with which you can reach with a cost of 10, let's say. And in my BFS, let's say this one came out first. This node came out first. And then I considered that, hey, I can move on to this cell, I can move on to this cell, I can move on to this cell. And I updated their costs to 10 now. Now, for these portals, do you think it will make any sense to apply the same operation of using the portal again? If you have already used one portal of the letter A, it is equivalent to saying that you have used all the portals, because now using the portal will make no sense, right? So you don't really need to go with the dummy node method, or if you want, you can just go with the dummy node method also, by creating a dummy node which would be connected to all of these cells. Or if you want, just do as the program had said, that for any letter, just apply the operation once and that's it. So the BFS, let me show you an example BFS. I will start from the top left. I will say that the neighbors are visitable in one operation. For now, let's say that there are no obstacles. And there is a portal present here, there is a portal present here, there is a portal present here, that's a portal present here, here, and so on. Then in the BFS, you will have these two nodes in the queue right now. Then let's say you have popped it out, so you got these two neighbors. For now, for this node, you have only one unvisited neighbor, so you will just say 2 here. Then for this node, you have a neighbor 2. You have a neighbor here, that is A. Let's say you mark that, hey, I can reach till this position with a cost of 2. Now, can I say that I can reach to all of these places with a cost of 2? Instead of just saying for this guy, I can say for all of these as well at the same time. Because after reaching here, I can always just use the portal, teleportation portal, to reach to those places, right? So I can actually, like, whenever I find a node having um, at character, I will just check, has this character appeared earlier also? If no, if the character has appeared for the first time, then in that case, just check out for all the neighbors you have for right now. Just tell everyone around this guy that hey, you can also reach in two operations. And then obviously it will do for its neighbors. Similarly, you can reach to this place in, oh, you could have reached here in three operations, not two. My bad. And for 3B also you can reach there in three operations. Then you will have you can reach here in three operations and you can reach here in three operations. Now for these people with the distance written as 3, you will say that hey, I can move here in three operations. I can sorry, hey, I can move here in four operations, four operations, four operations, four operations, four operations, four operations, four, 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 four. Right. Um, all of these cells might be reminding you of something like multi-source BFS. Though it's not really about multi-source BFS. So Dolly, is it fine now? I coded a similar solution and got TLE. I'm not sure of why is it getting a TLE. Um, maybe the constraints are a bit too tight because n is as big as 1e6. So if we are having a logarithmic factor along with big O of n, if we are having something like big O of n log n, then we might get a TLE because these 1e6 elements are not even in an array. These are in a matrix. So it would be a little slower than what we have in an array. And whenever we are accessing them, let me show you my code. In my code, I'm having, first of all, I just iterated over this complete matrix and stored all of the occurrences or the positions wherever the characters are coming up. So oc of 0, like OCC of 0 in this case, will tell me x comma y, or basically list of x comma y coordinates where matrix x comma y is equal to a. Fine. Similarly, OCC1 will have all occurrences of B and so on. By the way, during the contest, I had named this matrix to A because writing matrix again and again would take more time. Okay, so we have stored all of the occurrences of every character. Then this is the important stuff for the 0, 1 BFS. In a normal BFS, we do use a queue like this. But in 0, 1 BFS, we use a deck. So what happens is in normal BFS, for every new node, we insert it at the back. But in case of the 0, 1 BFS, if the cost from U to V is 0, then we just update dist of V as dist of U and insert this node V at the front. In case if the cost is 1, then it goes as you do in the normal BFS, insert at the back and dist V is equal to dist U plus 1. And as we like apply BFS or DFS on a matrix, we do like to have two variables dx dy just to make our life easier while coding. Basically, you can apply a normal DFS as you wish. Here I'm having a distance vector and I'm having a visited vector, which I think is needed in case of the in case of what do we say 0, 1 BFS. So I have created a visited vector. Oops. Yep, I have created this visited vector um, with size n into m plus 26. So basically for any cell x comma y, I will access visited of x into m plus y. It is like in the matrix I'm naming like this. So if there are 6 columns, then the cells will look like this. The numbers on the cells will look like this. That's why we are having x into m plus y. And in case if I'm talking about the dummy nodes, like I'm not creating dummy nodes for DFS, but I do need to mark whether I have whether I've used the portal at least once, like I have used the portal till now or not. So for that, I am using these extra 26 um, positions in the visited array. So for character A, I will just say visited of n into m plus the character minus A, which is gonna be basically um, 0 for the case of A. So you will have visited of n into m being used for A, n into m plus 1 being used for B, and so on. You could have created a different vector also if you wanted. Nextly, I'm having this initialization. I'm putting the node 0 into the queue. Then I'm copying the first element of the queue. I'm having this visited condition because something like this might happen. Like in case of a normal BFS, you don't need it. But as you need a visited array in case of Dijkstra, you do need it in case of 01 BFS as well, I guess. Adding it would never make anything worse for you. So it's up to you whether you want to add or not. I do say it's not bad at all. Nextly, I'm having the condition that if the current guy is having some character that has not been visited so far, then mark it visited. And for all the positions wherever this guy is coming, whereas wherever the same character is coming, just put all of them into the queue also. Put them at the front because you're having a cost of 0 for teleportation. After that, I'm talking about all the 4 neighbors in 4 directions. So find out the coordinates of the neighbors. In case if the neighbors are outside the grid or they're having some obstacles, then continue. If the neighbor is already having a path shorter or equal to the path that you are able to provide, then also continue. If you are able to provide a shorter path to the neighbor, then update it and push it into the queue. Um, and then I'm having the return statement at the end of the day. In case if the answer is not possible, then we have to return -1. Otherwise, we have to return the answer that we have got so far. How to pass from 2000 to 2200 rating mark on Leetcode? Any advice? In general, the main advice is just try to solve the problems that you can't solve right now. And for the problems that you are able to solve, try to figure out the time where you, like the mistakes you are making while solving the problem, due to which you are wasting a lot of time. Like in general, what happens is, if I take example of code forces, if I'm barely able to solve the D problem and I'm not able to solve E problem, in general, um, there is a chance that I might require 40 to 60 minutes on D problem or even higher. So after the contest, I can spend like 5-10 minutes at uh, like trying to remember what were the things I did think about during the contest for the D problem, and then try to think which one of them were worth and which ones of them actually wasted your time, and eventually you would know, uh, like whenever you would make a similar mistake in future, there is a chance that you might remember that this does not become fruitful for you. So you should have a different approach and all. Okay, so guys, please give me the feedback for the third problem right now. Is it making sense? Is it clear or not? To be honest, for the third problem, you have got to learn a lot of new things. For many people, it would be new. Like you got a big problem. You try to make it simple to think about the problem that you could have easily solved by a simple BFS. Since the weights are in general just 1 1 1 or 0, That's why we are thinking about BFS. Otherwise, we would have thought about Dijkstra. So if there are no portals, we could have applied BFS. Even if there are a lot of portals, we can just consider all of them as edges. We could not apply operation more than once, but does it really matter? Even if we apply more operations than one, try to figure it out. And you realize that, hey, it is never better to apply more than one operation. And in case, even if you could find out a situation where it was better to apply more operations, then the next idea for me would have been to think about the situations where it is better to apply one extra, like apply more operations than one, like in which situations it is better to do something like this. Nextly, since the weights can either be 0 or 1 for the moves that we are about to make, so you have to deal with, like, you can apply 0 1 BFS for dealing with 0 1 edges. And nextly, we are having too many edges, so we can do something like create some dummy nodes and connect these edges that were forming a click and just connect them to the dummy node. By the way, whenever you have a sub portion of a graph that in which all the nodes of this sub graph are connected to each other, we call this thing as a click. And to reduce the number of edges there, and like this kind of problems are not very common, but you will see this kind of problems once in a while where you take care of these clicks by creating a dummy node and connect the nodes with that dummy node. And it can vastly reduce the number of edges like this. Nextly, for this current problem, there is even faster, even simpler solution. That is, you don't need to use a dummy node. Instead, you know that whichever node you get first in your BFS, whichever node with the character A comes up first, you know that for all the nodes in the future, it is never beneficial to apply that operation, right? The operation is beneficial to be applied only once. So apply it only when you find out a node with the character A for the first time. Similarly, whenever you find a node with the character B for the first time, apply that operation of teleporting to all the other nodes and never else. So in that case, you can actually write a simpler code. You know, if you create those dummy nodes and consider them like the normal nodes, then you will have a more complicated solution, more complicated code at the very least. Just get rank under 300. I think you don't need that much for 2200 rating. Even if you get under 500, it would be fine, I guess. When I reached the 2600 rating, I was getting ranks around 2000, 200. Around 100 in the original leaderboard and 200 in the final leaderboard, including the Chinese participants. So it was enough to reach till 2600. So for 2200, it should be like around 500 rank, I believe, 500, 600. That should be enough. Maybe even 700. Okay. Does anybody want to ask any doubt for the C problem, or shall we move on to the D problem? You have 2 minutes for whatever doubt you want to ask. Then we will move on to the D problem. What's your rating? Uh, my rating was 2600 till today. I think it would be dropped by a lot now, because in today's contest, I spent like most of my time at debugging the C problem, and I still don't know what was the problem at that time. When I coded it up after the contest from scratch again, it did work in one go. And for the D problem, I just made a mistake of trying C problem for most of the time. If I had went to the D problem earlier, then I could have got a good rank. I wanna get to night. How much to rating 9 number of questions on average? I think for night, even if you are able to solve 3 problems, it should be enough. 2 problems might not be enough, but 3 problems should be enough, I think, in general. Sometimes the third problem is too difficult, like it comes up for the hard difficulty. So it's in general too difficult for nights. So even solving 2 problems fast might get you to night in those scenarios. Okay, so let's have a 2-minute break. Then we will go to the D problem. Okay, I'm back. Just 1 minute. Yeah. So let's talk about the D problem now. Today's D problem was mainly about implementation. So the problem says that we are being given an undirected weighted tree having n nodes from 0 to n minus 1, and we would be given all the edges, and the edges are weighted. Additionally, we are being given a lot of queries, wherein each query we are being given two source nodes and one destination node. We have to return an array answer of length equal to query length, where answer j is the minimum total weight of the subtree that is possible, such that it is possible to reach destination from both the source and destination, both the sources. Okay, basically the problem is, um, let me take one example here. Let's say you would be given a tree first of all. Nextly, in the tree, along with the tree, you would be given a lot of queries, where in each query you would be given three things: source 1, source 2, and the destination. You would be given these three things. Let's say this is the source one, this is the source two, and this is the destination. Then you want to find out the um, you want to find out the sum of edges, no? Yeah. You want to find out the minimum total weight, minimum total weight of all the edges in the um, basically from the given tree you have to figure out some subtree which has the minimum total weight of all the edges, right? So like you have this tree, you have to find out the smallest subtree such that you are able to move from both of these sources to the destination. You should be able to have reach there, and the total weight of the subtree should be as small as possible. So I think for the people who are coming for the D problem, it's pretty obvious that you would like to have only the nodes which are coming up in the either the path from source one to destination or the source two to destination, right? If there is some node or edge that is not in either of these paths, then don't include it in the subtree, right? Because if you include it in the subtree, it will just make the cost higher, which is bad for us. Um, so I hope at least this much is clear. It should be pretty obvious for the ones who are coming at the D problem. So the next thing is all you want to do is find out the total weight of all the nodes which are coming up either in the path from source to destination or source two to destination. That is the goal. So if you have a tree, you might have a situation like here is the source one, source two, let's say S1, S2, and you have a destination, let's say T1, or let's just say it as T target. So in case if the paths are completely different from source to destination, then there is no problem. Just the answer would be sum of all of these edges and sum of all of these edges, right? This is the case one and the simplest possible case. Then you have a more complicated case where you might have something like this: source one, source two, and destination. So basically the whole path of source one is coming up in the path of source two also. So solution, like the answer would not be the sum of this and sum of this. The answer would be just this much. Because if you take just this much subtree, source one is also able to reach to the target and source three is also able to reach to the target. So let's say if the weights are 5 and 5, the answer would be 10 and not 15 here. These two are very obvious cases, है ना? Once you think about this key source to destination, source to destination. And one more thing, which should be quite obvious right now, is we need to use binary lifting or something like that. Since we will have a lot of queries and in every query we'll have to find out the sum of path or something. So guys, this is a prerequisite. You should know about binary lifting. You should be able to find out sum of paths using binary lifting. So yeah, we are clear till this point. Now, in my case, I was pretty lucky that within like 2-3 minutes or 5 minutes, I had got to the I had got an approach in my mind. I was thinking about this on these lines only, that maybe there can be no overlap, maybe there can be overlap, but if there is an overlap, I would have to figure out how to deduct that or something. One idea that I had in mind was the something like this might happen. There is some unique part and some um, overlapping part from the path from S1 and S2 to destination. So for this case, I thought that maybe if I could just count the distance from S1 to T and then for the distance from S2 to T, if I could just figure out how much of the path is overlapping between with this. And like this was the idea that I was having, and I could not think of a good way. But one thing that came in my mind was um maybe from S1 to S2 and from S2 to T, maybe I could have an LCA in the middle. If I'm having an LCA of S1 and S2 coming up in the middle while going to T, then obviously this much path would be unique to both of them, and rest of the path would be definitely overlapping for both of them. Right, in case if LCA is coming up for both of these people in the path. So the idea was like I started to think about this, that hey, I will count, like I will find the LCA of both of these nodes here, and then count this, like find out the cost of this path separately, and then the costs of these paths separately. This was the next thing that came up in my mind. Then I again started to think a little, and then what I realized is there can be a scenario like this one also. You are having source 1, source 2, and the target is here. So basically, the path from S1 to T is this, and the path from S2 to T is this. Right. So this is the overlapping area. This is the overlapping area, and both of these, like all of this, has to be calculated only once. Right. Um, so if I try to apply the same logic of um, finding path from LCA to the target, like there is one thing that I realized at this point, that is no matter wherever the target is, no matter wherever the target is, whether it's an ancestor of the LCA, or if it is a descendant of the LCA, or if it is the LCA itself, whatever the case is, for for one of these nodes, at least one of these nodes, I will definitely have the path from LCA to target come up. Like whether this is a descendant, even in that case, I will have to go through the LCA from S2 to T. Whether this node T came up somewhere here, I would have, in that case, I would have to pass through the LCA of these two nodes to go from S to T. If it came up as an ancestor, still you have to pass on through the LCA. Yep. So main observation here is that I do need to pass through the LCA in all the scenarios, no matter where the target is. Even if I have a case like node S1 being an ancestor or a descendant of the other node, even in that case, this is the LCA, so I still have to pass on through the LCA for at least one of the nodes to go to the target, right? Even if the target is a descendant, you still have to pass on this through this node because S1 is the LCA itself. So in a nutshell, what I concluded from here is I can consider this as one component of my answer. Consider it as one component of my answer. Now the other components are the path from S1 to T, which does not conflict with this. Basically, if T is an ancestor of this guy, in that case, I will just count this much path, right? Like in um oh wait, I think I'm missing out one thing. Oh no, 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 it's fine. It's fine. I was just verifying whether my solution has a bug or not. It doesn't have it. Yeah. So my next intuition, as I was discussing, was that if okay, for now let's call this node as L because we would be using it again and again. So if the target is an ancestor of L, in that case, I would have to count the sum of both this path and this path as well. I would need both of these in the subtree. In case if the target is not an ancestor but it is a descendant, then for the node S1, can I say that I have to count only this much path? I have to count the sum of only this much area, this much path. And for S2, I have to count all of this. So for this, the idea that I came up with was that let's find out the LCA of these two people. It came out to be this point. You know, this is the point that is the LCA of S1 and T. So if this LCA, in case if this LCA is above L, like if this guy is an ancestor of S, then this will come up above, right? It will come above. So this LCA would have um, a higher level. This will be coming up above the and node L. So in that case, I will count the path only till the, like I will count only the sum of all edges from S1 to L. And in case if the LCA is coming up um, below the node L, then I would have found the node uh, till which I have to find the sum. Right. I have to find the sum from S1 to the LCA of S1 and T. Right. This one is nothing but the LCA of S1 and T. So I will calculate the nodes like this node. I will find out this node and will add this sum. In case if this is below the LCA, if it is above the LCA, then I will count this area. Not talking about the other node for the case when T is a descendant. In case if T was an ancestor, then like similar to the way I was calculating LC here, I will calculate the LC here also, because I don't know which side this node T is coming, whether it is here or here. So obviously I will count the LCA for both of them. Now I would have got the, let's say, LCA at this place itself. Then I can actually luckily apply the same logic here also, that here the both of the LCAs are same, so it doesn't really matter what we do. Just add this area. So basic algorithm that I created from here was, for every query, find L equal to LCA of S1 comma S2. I'm naming this LCA as L. Then what I will do is um, find LCA of S1T and LCA of S2 and T also. Okay. Now, one component that I will definitely have as my answer is the path from L to T will definitely come there, right? No matter where the node T is, this will definitely come up in the answer. Nextly, depending upon whether T is higher or L is higher in the tree, my answer will depend, like whether I should contribute this or this. So if T is higher, if the target is higher, in that case, I will contribute the path from S1 to L. Otherwise, I will contribute the path from S1 to LCA of, for now, I'm just naming it as LC. Basically, I'm talking about this LCA of S1 and T. Similar logic for the third guy. If T is higher, then there is no problem. Just take the path from S2 to L. Otherwise, path from S2 to LCA of S2 and T. That's it. Add these three components. For finding out the sum of the paths here, it can be done very easily via via binary lifting. You can have your own template, or you can just write the code on the spot. The code for LC binary lifting is not too big. Like it's big in terms of the like content, but For the logic part, it's almost always the same for most of the code. So you can write it pretty fast. And for finding out the path sum from L to LCA of S1 and T, first of all, you will have to calculate the LCA, then you can find out the path easily. So that's it for the logic. The code looks like this. I computed the adjacency list first. After that, I initialized variables for my binary lifting. I applied a DFS algorithm to find out the values of the parent array, the level array, and some array that I would use for binary lifting. That's actually the normal stuff. If you have done a few problems on binary lifting, then you would be able to understand it. If you have not done a few problems on binary lifting, then one thing you can do is try to understand my code, like read the code, try to understand it, and learn from here, or just go to some tutorial and learn about binary lifting first, do some practice, and then come back. Nextly, I'm initializing all the other values of variables that would be used for binary lifting. That is basically building the array for binary lifting. Then I have a function created left that would be used for uh, finding out the kth ancestor or the sum of the uh, edges from the path from current node to the kth ancestor. This function will do both of these things. Nextly, I have a function with name LCA. It will find out the sum of all the edges in the path from U to V, and it will return the LCA of the nodes U and V as well. It will do both of the things in one function. Nextly, I created a solve query function that I will call for every query, where this is one component I have, LCA LT1, that will basically return me the sum of all the nodes from L to T. Then I'm having the part of finding the LCA from a source node to the target, that is the destination node. And depending upon whether the node L is higher or the node, um, the LCA of U and T is higher, I will return the sum depending upon that. And that's it. By the way, one thing that you might like to notice is that I have converted the code into one-based indexing, the variables to one-based indexing, so that I will not have to write if else conditions for like in binary lifting right now. I'm having a node 0 as a dummy node, which I have just set up as the parent of the root node, that is 1. In case if you keep the root node as 0 in zero-based indexing, then most probably you will have an imaginary node with value -1, with which everything would be initialized initially. So you will have to write some if-else conditions at various points, which we don't need to write because um, I'm having one-based indexing. So this is one good thing that you can learn about, and that's it. The implementation is not too complicated if you have implemented binary lifting a few times. Like in my case, I have implemented the logic of binary lifting a lot of times. So in general, I am able to write up the logic in one go, um, from this point to um, till this point of writing LCA. All of this is something I don't have to think much. I can just write directly. Um, and I had to think only for this much. And you can have a template for all of this. So if you have a template, then you can do it very fast. Did you use the function LCA u comma v comma r where you calculate LCA of u with r is root? No, I'm having a fixed root. Like it doesn't matter which node is the root, so I just fix the node 1 as the root. Like I just consider node 1 as the root. Guys, anything else? I saw some solution that used this function. I'm not sure. Maybe um, I'm not 100% sure, but maybe this is something we can do in HLD or not. Maybe not in HLD, but in I don't know. No. Like I also feel that I have heard, like I have read about this kind of logic somewhere. Apparently, Jiangli has a code like this. I don't know. I think that at the end of the day, he would also use a fixed route, I believe. Anyways, I've never got into a problem where I needed to have a flexible route. So, anything else? And sorry for the B problem in case if someone is listening right now. For the B problem, I just messed up at the preparation. Like before the PCD, when I was thinking the way in which I will explain, there was some part that I felt that it should be very natural. It should be obvious enough. But during the PCD, I felt that um, it might not look natural to a lot of people. And I tried to over explain it, and um, the PCD just got confusing in that case. So that is why I started the B problems explanation from scratch again. And after the PCD, we will trim that part so that the new audience that would watch the recording will not have to watch the words explanation. Okay, you just draw it LCA U comma V LCA U V comma to get the new LCA with R is root. I don't get how it. Oh, nice. Okay, it looks something cool. Um, I don't know, and UV, VR, and UR. Okay. Hey, wait. I don't think it should work. Like, how is Zoring gonna help? You can have any values for the nodes UV and R. LCA can be anything. Okay, maybe it might be an yeah, it might be a nice thing. I'm able to visualize something. Maybe the idea is something like LCA of UV, LCA of UR, and LCA of VR. Maybe it has something to do with two of these will have the same value and one of these will have a different value. Maybe something like this might happen. Because if R is an ancestor for some place where like LCA of U and V is this, LCA of U and R is this, and the LCA of V of R is also this. So it will just get cancelled out. And if R, let's say, happened somewhere around this point, no, even in this case, maybe R, let's say, lies somewhere here. So in that scenario, U and R will have this is the LCA, and for V and R or U and V will have this is the LCA which will get cancelled out. So it will come out to be the LCA. Yep, so it looks good. Yeah, exactly. It removes the duplicate. Anyways, uh, anything else? And what about the other people? I don't think anyone else is watching right now. Though. The bad part is that for the B problem, some people might be watching the explanation which should be removed. So like they will just get their time wasted until the processing is done on YouTube. Okay, so shall we end? Oh, wait. You used it as a black box. So did it actually help in some way? Um, you have the destination that you want to reach, and you have the nodes, let's say U and V, or maybe. Okay, nice. If you consider this guy as the root, then in that case, this will become the new LCA. The part other than the LCA would be actually something that does not occur. And this part should also come just once. Okay, this makes it a lot simpler. Yeah, nice approach. Yeah, got it, got it. That's a really good approach. I actually never knew that we can do something like this of LCA UVR. I never had something like this in mind, so I never had this idea that uh, you can consider the destination node as the root, and then the LCA part would be common in both of them, and the other part would be coming exactly once. So all we have to do is just add up the distance from destination to U, add up the distance from destination to V, and subtract this once from destination to LCA. Or maybe do it in this way: destination to LCA, LCA to U, and LCA to V. I don't understand how that XOR thing works though. Um, I also don't know how somebody would have thought, but um, like if we try to prove it wrong, we can see that it is actually working really well. So if this new node that you want to make as a root is above the LCA, then in that case, um, for the LCA of UR and LCA of VR, R will definitely come as the LCA and nothing will change. Like even for this root, you will still have this node as the LCA. That is something which should happen, which should happen also. You know, basically, if R is not coming in the path from U to L or from U to V, or it's not coming in the path from U to R basically, then LC will remain the same or it may change. Yeah, it can change. It can change. If R is in the path from, not in the path, but I don't know how to generalize this thing, but I'm able to visualize this part that if R is not in this area and it is anywhere other than this area, basically if it is not in these two subtrees, then the LCA will still remain the same and both of these will just get cut out. Nothing will cause us any trouble. If R comes up in this subtree, then the LCA should change. This guy will not remain the LCA anymore. The LCA would be the LCA of U and V actually. The new LCA of U and V would be the LCA of U and R. है ना? And because of the way we have written the code, like we are writing the code here, the LCA of U and V and the LCA of R and V should be the same thing and it should get cancelled out. This guy should just cancelled out in that case. So LCA would be updated to this branch. Okay, easy to visualize, but I don't know how somebody would have got this idea by himself. Hi, in general, what's up, research from Jiangli? Yeah, though it's not mandatory, Jiangli would have got this idea. This might have been invented by someone and then everybody started using it. This is possible. So was answer is equal to distance of u comma v plus distance of u comma d plus distance of v comma d by 2. This also works basically. We checks occurs twice, so you divide by 2. Okay, that's also a clever technique. Okay, if the D is up, count this once, count this once, count it once. Nice. Count it once, count it once, and count this one. Nice. Cool idea. Okay, so looks like my idea was the most difficult one to understand, or the worst solution maybe. Though my solution also did not take much time. In my case, like during the contest, when I saw the problem, it took me barely 5 minutes to get the idea. So it also don't have much of a um, casework, but there is a higher chance of getting missing out some case in comparison to the solutions that you have shared. The ones you have shared are better. Okay, so shall we end the stream now? It's already around 2 p.m. now. It's quite late. No, no, you actually shared good solutions, the better solutions than mine. In case if it was a problem with easier difficulty, then I might have tried to think a little more to have a simplified casework. But I was expecting a difficult problem at the D position, and as soon as I got this idea, I thought that hey, this might be the intended solution. Okay, if I had seen the solutions before the PCD, then the explanation of D could have been simpler. Okay, shall we end? The only reason I'm a little hasty right now is because we need to trim the part of the B problems explanation as soon as possible. Okay, no messages for the last 2 minutes. Bye.